We're living in this really fascinating moment. There are two just massive, fundamental shifts in computing happening all at the same time. One of them, artificial intelligence. Well, that's already reshaping our daily lives. The other, quantum computing, is poised to completely rewrite the rules of what's even possible to calculate. So the big question is, what happens when these two forces collide? And no, this isn't some far-off sci-fi dream. It's a field of research that's happening right now. And it's creating this powerful synergy that could just push technology forward in ways we're only just beginning to imagine. So on one side, you've got AI. You can kind of think of it like this neural network here. It's always learning. And on the other side, you have quantum computing, represented here by the qubit, which plays by these really strange and incredibly powerful rules of quantum mechanics. Now, the really key thing to get here is that this isn't a story of competition. It's a story of collaboration. All right, so here's our game plan for understanding this collision of revolutions. We'll start by framing the partnership. Then we're going to look at how quantum helps AI, how AI helps quantum, and where this whole thing will actually make a difference in the real world. And finally, we'll touch on the major challenges and, what the road ahead looks like.
Okay, first things first. Let's get one big misconception out of the way right from the start. This is not about quantum computers replacing the AI we use today. The reality is actually way more interesting than that.
Instead, you should think of it like a powerful feedback loop. Quantum computing is going to turbocharge AI, and at the very same time, AI is becoming absolutely essential for building better quantum computers. Each one pushes the other forward, creating this cycle of innovation that just gets faster and faster. And to see why this partnership is so powerful, we really need to get the fundamental differences between them. Your laptop, your phone, they use bits. They're either a 0 or a 1. Simple, right? Well, a quantum computer uses qubits. And get this, thanks to a wild quantum property called superposition, a qubit can be a 0, a 1, or kind of a blend of both at the same time. This means quantum computers can explore tons of possibilities at once, which makes them brilliant for these very specific, super complex tasks that would just choke a classical computer.
Okay, so let's dive into that first half of the feedback loop. What does quantum power actually do for AI? This is where things get really, really exciting for anyone working in machine learning.
Just think about the absolute toughest problems for AI today. They're usually problems of just immense complexity. It's like trying to find a single needle of insight in a universe-sized haystack of data. A classical computer has to check one piece of hay at a time. But quantum computing, because it can explore so many possibilities at once, is basically built to solve exactly these kinds of impossible puzzles.
So picture this. It's a classic problem for AI. Imagine you have two groups of data, but you just can't draw a simple straight line to separate them. The pattern is way too complex. This is exactly where classical machine learning models can really, really struggle. So how does quantum solve this? Well, it pulls off what is basically a computational magic trick. By mapping that messy, flat data into a higher dimension, the pattern suddenly becomes obvious. Now, a simple plane can just slice right through and separate the two groups. Quantum computers can do this on a massive scale, finding hidden patterns in dimensions that are just completely inaccessible to classical AI. It's pretty amazing. So what's the bottom line for AI? Well, it's absolutely huge. We're talking about training models faster, using less data, and getting way more accurate results. It's about breaking through the bottlenecks in all those complex optimization and search problems. It's essentially like giving AI a whole new toolkit of superpowers.
But remember, this is a two-way street. AI isn't just getting a boost from quantum computing. It's also a critical tool that we need to build the quantum future in the first place.
I mean, building and operating a quantum computer is one of the hardest engineering challenges humans have ever taken on. Qubits are unbelievably fragile. They're sensitive to the tiniest disturbance from heat or even a small vibration. And this is where AI steps in, not as some future promise, but as a technology that researchers are using today to make real progress. So how exactly is AI helping? Well, it's playing a bunch of key roles. It can discover new quantum algorithms that a human might never even think of. It can optimize the physical layout of quantum circuits. It can automate the endless tiny calibrations these machines need to stay stable. And maybe most importantly, it's helping us design the error correction that is absolutely essential for taming the noisy, fragile nature of today's quantum hardware.
Okay, so we've seen how these two technologies help each other out. But what does that actually mean for us? Where is this partnership going to make a real-world difference?
Well, the synergy between them unlocks a whole new set of advantages. Yeah, you get higher speeds and better precision, of course, but the real game changer is what this slide calls complex task analysis. And what that really means is we can finally start to model the world as it actually is, in all its messy, beautiful complexity, without having to simplify everything just so our computers can keep up. And that applies to everything, whether it's a new drug molecule, a global financial market, or our planet's climate.
In healthcare, the potential is just staggering. We could simulate new molecules to discover life-saving drugs in a fraction of the time it takes today. We could analyze incredibly complex DNA sequences to understand diseases better, or enhance medical imaging to spot problems earlier and with much more accuracy.
And it goes way beyond medicine. This partnership could help us discover new materials for better batteries or more efficient solar panels. It could solve these mind-bendingly complex optimization problems for global shipping routes or for financial portfolios. And it could help us build far more accurate climate models to better understand and predict changes happening to our planet.
All right, so as amazing as all this sounds, we definitely need a little reality check. We are still in the very, very early days of this journey, and the road ahead is full of some truly massive scientific and engineering hurdles.
And these hurdles are significant. They kind of fall into a few main buckets. On the hardware side, you've got fundamental problems like system instability and interference from the outside world. The quantum world is just incredibly fragile. Then you have the application challenges, finding the right problems where this hybrid approach gives a real advantage. And finally, there are the deep integration issues of just getting these two very different worlds to speak the same language. Let's dig into that a little. On the hardware side, the biggest enemy is something called decoherence. And that's basically when a qubit loses its special quantum magic and just becomes a regular old bit because of tiny vibrations or temperature changes. On the software side, we're still figuring out the best ways to translate our classical data into a quantum format, and how to avoid these things called barren plateaus, which is a strange phenomenon where a quantum AI model can just stop learning for no obvious reason at all. But the good news is, researchers have a roadmap. In the short term, say the next 3 to 5 years, the goals are to use AI to find better ways to run existing quantum algorithms and show some real utility in fields like chemistry. Midterm, maybe 5 to 10 years out, the focus is on building robust hybrid systems and getting much better at that error correction problem. And the long-term vision? Well, that's where we start to see fully quantum AI, and even using AI to help co-design the quantum hardware of the future.
So as we wrap this up, it's pretty clear that combining AI and quantum computing isn't just about getting faster answers to old problems. It's about enabling a completely new kind of learning, one that might just change our very definition of what intelligence even is.
And this brings us to one final, really provocative thought. Today, our AIs learn from classical data. Pictures, text, numbers. But what happens when we build a quantum AI that learns directly from quantum data, from the state of a quantum system itself? What new kinds of patterns could it possibly see in the fabric of reality? And what would that force us to reconsider about the very definition of learning itself?